Okay, hi everyone. Welcome back to the second class. Just maybe a very brief recap from what we did last time. We introduced this problem of computing a maximum flow in a flow network. We said it has many different applications, from Soviet's railway systems to computational biology. And we want to find sort of the maximum flow from a dedicated source vertex to a dedicated sink vertex. And then we had sort of an initial idea how to do that. We had this iterative scheme where we started from a zero flow, and then in each iteration would find or look for a path from source to sink along which we can increase the flow. This initially did not work since we were looking for such a path from S to T. But then we soon realized that once we introduce these revert edges, these red edges that sort of tell us how much flow we have already pushed and how much we can undo in the reverse direction. If we create such a residual network, then we can actually find such an augmenting path and ended up with a much better flow, which in that example that we looked at was actually optimal. So we found the optimal maximum flow in this particular example. We don't know yet if this will always work, but I guess, yeah, we're hoping that this is sort of a good approach, and we'll see that this actually, in fact, is later. So then we started with this example that is shown right here. We started from a flow network, and we sort of played this Ford Fulkerson idea. We always created the residual network, looked for an ST path, used this residual capacity of this path to increase the flow, and then updated the network in each iteration. This is where we stopped. We were almost done with this algorithm. I think there's like one or two iterations missing, and I want to start by showing this. So this was our final residual network. Let's check if this is true. So this was our final, this is the original network. And I'm showing the flow in blue. This is from last time. And so just to double check, if you look at this edge, for example, we see that we have a flow of 11. So this leaves capacity of 2 in this direction. And it gives us this residual capacity of 11 in the reverse direction. Same is true here. Out of this 14, we have 3 left, since we already pushed 11 units. Here we pushed 7 units. Oh, sorry. Here we pushed 7 units of flow. So this edge in this direction is gone, but in the reverse direction, we can undo 7 units of flow. Here we have 13 left out of 20. And here nothing's left out of the 4, but we can of course undo 4 units of flow. So this seems to be correct. So at this stage, we want to find a augmenting path, meaning a path from S to T, the source to the sink in this new residual network that corresponds to our current flow. The value of the current flow is 11, and this is what we would like to increase. We're trying to look for So we're trying to look for an augmenting path from this node here to this node. And we could pick, for example, this particular path. If you walk from, let me copy this first, I don't have to redraw this later. So we could walk along this path here, from here to T. And this is clearly an augmenting path with residual capacity. Any suggestions what the residual capacity should be of that? Should this path have be? Any? Yeah, 12 exactly, because it's the minimum capacity of any edge on this path. So the residual capacity CF of this path is equal to 12. Okay, so let's augment, or let's increase the value of our flow based on this augmenting path. So let's push another 12 units along this path. So this means, and I'm indicating this in blue again in the original network. So we would have 12 units on this edge. Out of 16, we would have 12 here. And we already had 7 here, so we will have now 19 units. So let me just remove the 7. And this will be 19 units of flow. Okay, so this is our new flow. And what's the value of this flow? just to warm as a little warm up. What's the value of this flow, of this new flow? Does anyone remember the definition of the? It's 23. And why? Because the value of the flow is simply defined as the sum of the flow that is leaving our source node, which in this case is 12 plus 11, which is equal to 23. So the value of that flow now is 23. So, and then the final step is, I mean, you will see this is the final step. In general, the next step would be to now sort of modify the residual network. So I'm cheating here a little bit. I'm taking the previous residual network and I try to update this residual network based on the new flow, in particular, based on the flow that we have pushed along this path. So how does this look like? We have, in this case, residual capacity 16. Now we have pushed 12 units, so 4 units will be left here. So we have residual capacity 4. And we have nothing left on this one. This was our so-called critical edge. We haven't introduced this terminology, and this is not really important. But this is sort of the edge that gets lost because the capacity of that edge was equal to the critical capacity, of the residual capacity of this path. So this edge disappears. And 13 means that 1 unit will be left on this edge. And of course, we have also said we introduced these reverse edges. The reverse edges reflect how much flow we have already pushed along a certain path. Here, we have pushed 12 units just now. So we'll have residual capacity 12. Same here. We have 12 units of capacity here. On this edge here, we had already 7 units of residual capacity. So we are increasing this by 12 units. So we'll have 19 units of residual capacity here. And that should be it. And 1 unit is left here. Exactly, this is correct. So this is the 1 unit that is left of this initial 20 units of capacity. And what happens now? Now we're trying to do the same thing as before. This is our new updated residual network. Let me make this a bit nicer here. Which missing? Yeah, it's not really nicer. But this is our new residual network. And now the question is, can we find another augmenting path in this network? And unless I did some mistake, there shouldn't be any. So we can start walking from here, from S along this edge, and we get stuck. Everything is just entering this vertex, but nothing's leaving. We can also alternatively walk along here and then continue here, and it gets sort of stuck at the same position. Or we could just continue walking along this edge and again get stuck because all other vertices are entering this vertex. So we won't find any augmenting path anymore in this new residual network, and this is where the algorithm terminates. Hopefully with an optimal maximum flow. It's not a surprise that this is the case, but we're gonna show this later. So this is our final network and our final flow, and the point where the algorithm terminates with a flow of and returns a flow of value 23. This is our final answer to this example instance. And before we look at whether this actually is the flow that we're seeking, I mean the maximum possible, let's have a quick look at the performance of the algorithm. So how efficient is this? And the first critical observation to make here is that with every iteration, you're strictly improving the current value of the flow, right? You're finding sort of a ST path, and these edges exist only if they have non-zero capacities left. So we will always be able to strictly increase the value of the flow. So the flow will be increasing in every iteration. And this sounds like an obvious observation, but it's of course important for proving termination and also for proving running time later. So let's write this down. Notes on performance. Or are there any questions to the example? Or everything clear? Are you still mentally in spring break? No. Did anyone travel in spring break? Yeah. Who traveled in spring break? Okay, so Did anyone travel to the north or everyone to the south? North also, okay. I thought we were the only ones. We went to Canada, but only because we had to for visa issues. Yeah, but I guess mostly what we always see, when we see reports in Germany on TV, then we usually see, because we don't have spring break, we always see then US students and they, in our cliche world, they all go to Cancun and celebrate spring break. I don't know if this is true. But I'm sure if you have the opportunity, you would probably travel south, not north. Anyway, back to Fort Fulkerson. So notes on performance. First observation that we made is that the flow increases. And by how much does it increase in every iteration? We can actually specify the amount by how much the flow increases in each iteration. I mean, amount not in terms of a number, but by a variable. Yeah. Oh, sorry. Into the example or in general? Yeah, then let me try this. So by how much does it increase in each iteration? Any idea? Yeah. Yeah, the residual, exactly. CF is the residual capacity of the path of the current augmenting path. So this is our first observation. The flow increases by CF of P after each iteration of the while loop. But critically, the actual performance of the algorithm will depend on your strategy, how you find this path. Because we haven't talked about this at all so far. I only have shown you magically this green path here, just by looking at it. But of course, this was a bigger, more complicated instance. You can't do this just by looking at it, but you do this with an algorithm, and the choice that you make there will affect ultimately the performance of your algorithm. Okay, so the performance depends on how you find the augmenting paths. And in particular, so there's like a bad case or a bad scenario actually, where you can show that there is a sort of a poor choice of an augmenting path, which will lead to your algorithm not terminating, because the value, I mean, you will still strictly increase the value of the flow in each iteration, but it will not converge to even the maximum value. And therefore, this algorithm will actually not even terminate if you're unlucky. So there's some choices. Some choices can be poor in this sense. So some choices can be poor. Cause the algorithm not to terminate. But the good news is, if you have integral capacities, if your capacities are integer values, then you don't have to worry about this. Any strategy will work, and the algorithm will terminate, and it will terminate in a specific running time that I'm going to write down first before I explain it. And this is the case very often in practice, that these capacities are integer values or rational values that you can scale to integer values. So in these cases, you don't have to worry about termination of the algorithm. So for integer capacities, running time is order, I'll write this down first, number of edges times the value of the optimal flow, F star. I indicate this by F star. Let me just mark this. So F star is maximum flow value. And E is the number of edges in our graph. How can we see that? So it's an iterative scheme, and the running time of the algorithm will be proportional A to the number of iterations that you require, and of course the time that you require in each iteration. In terms of number of iterations, we said that in each iteration we're strictly increasing the value of the flow, and if these capacities are integer values, then actually we increase it in each iteration by a unit, by at least a value of one unit, and that means that we need at most F star many iterations of this algorithm until we hit sort of this maximum possible value. So F star tells us something about the number of iterations we need. And in each iteration, the main sort of the critical thing that you have to do is finding a path from S to T in the residual network. And you can do this using your favorite algorithm, either BFS or DFS, anything that finds sort of a path from S to T. And this takes time, as you have learned already, order m plus n. In our case, since we have a graph in which every node lies on an ST path, and in particular, every node has at least one incoming edge, we know that the number of edges is at least the number of nodes minus one. And therefore, we can sort of say that the order of m plus n is the same as the order of just simply m. So I think this might be confusing. I'm using m plus n here for number of edges and number of nodes instead of e. So instead of saying the number of nodes plus the number of edges, I'm just saying the order in terms of the number of edges. This is the only thing we need, since our number of edges are lower bounded by the number of nodes. So the running time per iteration is simply speaking DFS or BFS in a connected network, and the number of iterations we need is bounded by the value of the maximum flow in this network. Any questions about that? Does it make sense? So I think the running time of BFS should be clear by now, but let me just state the fact why we have F star many iterations. So the critical insight here is simply that the flow increases by at least one unit in each iteration. So we see this increase by at least 1 unit each iteration. And this doesn't really concern sort of the exact actual performance of the algorithm, but it's still an important note to make at this point. We're not going to show this, but an important fact is that if we have these integer capacities and we run for Fulkerson, then we will actually end up also with an integer flow. So every flow that we assign to these edges will also have integral values. And it's a very nice property and an important property, so I'm going to write this down here. So for integer capacities, FUV will be also integer. For pairs of vertices in our graph. Okay, so again, this doesn't really affect our performance here, but it's an important insight or important property that if we run this algorithm for Fulkerson with integer capacities, we'll also end up with a flow of integer values. So that's nice. So we don't have to worry about this as long as we have integer capacities. The running time seems okay, but F star can be very large, of course. And there's an example in the Corman book that gives an example with F star, meaning the value of the maximum flow being, I think, 2 million, definitely very large. And there are choices that there's a way that you can make choices such that the flow increases really by only 1 unit in each iteration, meaning that you really would have to spend 2 million iterations in this algorithm. And this is, you can imagine, it's not really, not very efficient. And therefore, there's alternatives. In particular, in the form of what's called the Edmonds-Korp algorithm. an Edmonds Korb algorithm is really exactly what we have described so far, for Fulkerson, but using BFS to find the augmenting path, meaning the path with the fewest edges, the shortest path in terms of number of edges in your graph. And then you will see that we have sort of a better guarantee in terms of running time. And so this is the famous Edmonds Korb algorithm. So this algorithm, again, is just Ford Fulkerson, FF, I think we call it, plus BFS for finding the augmenting path. What one can show, but we won't do this in this class, is that the running time of this algorithm then will be order number of nodes times number of edges squared. So I'll try to avoid this flipping between E and M, just in case this happens. When I talk about M and N in this context in graphs, M will always be the number of edges and N always the number of nodes, but I'll try to be consistent here. So V, the number of vertices, times number of edges squared will be the running time of this algorithm. This can be seen in the Corman book on pages 7 to 7. The basic observation there will be that you have still in each iteration you're running BFS. We said this takes time order E, the number of edges, as before. And the number of iterations you can then bound by number of nodes times number of edges, which gives overall number of nodes times number of edges square running time. The way you show this is basically by bounding the number of times each edge can be the so-called critical edge, meaning the edge with the minimum capacity on an augmenting path. But we're not gonna show this. So this is basically what you can see in the Corman book. So if you're interested, it's shown in Corman, page 7 to 7. But for now, the only thing to know is really there is an alternative. You don't have to rely on an algorithm that depends on the value of the maximum flow, but really only on your input graph. And the only thing you have to do for this is always finding the shortest path in your augmenting path using, for example, BFS. Okay. Okay, so that's the running time. This is all we're going to talk about, the running time on this relatively high level. Yeah, not more important, but at least as important as the running time is, of course, the correctness, in the sense that once we terminate, once we cannot find, as in this previous example, as we cannot find any augmenting path anymore in the residual network, are we actually getting sort of the optimal path, the optimal maximum flow? So is the flow that we're returning actually maximal? In our case, the question is basically if the value of 23 is the best possible value of a flow in this particular network. So this is the question that we're sort of considering for the rest of today's class. Yeah, there's a question. Yeah, number of edges. There's no weights. No, there's no, yeah, in terms of the number of, so unit distance, so you assign a distance of 1 on every edge, essentially, conceptually. Yeah, correct. Any other question? So the way we want to show this, I mean, high level speaking, that's the flow that we end up with is optimal, is using a very common strategy. We try to find something that we can prove as an upper bound on the maximum flow. And then we show that actually we can find one instance where these two matches, ready to match in the sense that lower bound equal upper bound, and we know that this is sort of an optimal flow, very high level speaking. So for that, does anyone have a suggestion what we could look at if you want to have an upper bound on the maximum possible flow in a network? So if I give you a network and you see the graph and you see capacities, thinking about the definition of a flow and the value of a flow, could you tell me immediately sort of an upper bound? Oh yeah, here's the largest edge weight. I had the same answer in the previous class, but you can have multiple paths, so this is not really an upper bound. Yeah. And with weight, you mean what? Yeah. What do we mean? What do we mean with weights? So we don't have weights. You mean the capacities, or not the flow weight, not the flow, right? No, I mean we assign flow values on these edges, but actually at this point we don't have a flow. We just have a network with capacities, and I guess we're assuming that what you mean is we're summing up the capacities leaving a certain node, right? The source node. Yeah, it's correct. So that's exactly true, and this is true because this is the definition of a flow value. It's simply the sum of the flow values that leave our source vertex, and we know by our capacity constraints that every flow can, at most be the capacity of that edge. So if you just sum up the capacities of these edges leaving S, then this is something that upper bounds the value of a flow. And this is true, and it can be a very weak bound. There's a better way to do this, and this generalization of exactly this idea of having sort of edges or the capacity of edges leaving S or leaving something more general will lead to what we call graph cuts. Who has heard of graph cuts or cuts in graphs? You have. In what class do you do that? Or was this in this class? You heard of cuts? Oh, yeah. In what lecture was it, over the topic? Last semester. Okay. For this. Okay. All right. So, and there's general versions of cuts, but here we're interested in specific cuts, namely ST cuts, where we partition a set of nodes into two sets, and one set will contain the source, and the other set will contain the sink. So let me just write this down. Let me first write down sort of the overall observation, and for this I would like to take the same example if possible. So let's see, just to visualize sort of this initial idea and sort of visualize a possible generalization of this idea. Basically, what you have said is we could take S, the source. No, we can take the source and then look at all edges that leave that source, and this is an upper bound, taking the capacities of these edges. Now we could sort of generalize this idea to a larger set of nodes, and instead of just taking S, take a node set in our graph that contains S. For example, this one, we call this L. And let's take another, and let's take sort of and put all other nodes that remain into another set that we call R. Then this is sort of a node partition. And vaguely speaking, again, as before, every edge, let's say, differently. If you look at the flow that goes from S to T, any such flow has to cross these two sets of vertices from L to R, and it will eat up some of the capacity of the edges leading from the left set of nodes to the right set of nodes. All these edges here going from left to right, these capacities intuitively will somehow, as we will see, upper bound every possible flow that we can send from S to T. And this intuitively should be true for any cut. So whenever you sort of split your vertices into two sets, all edges that cross this cut will define sort of an upper bound on the flow that you have. And before we had sort of seen a special case, or your suggestion was a special case in which we sort of contained, or which we had a set of nodes that contained only S and took all other sets as the remaining set R. So let's just quickly write down this observation. So this is what we call graph cuts. Is this blue? Yes. About graph cuts, you can again read a bit more in Corman. Just give you the reference for this. Okay, but the observation, again, to summarize this, is, and this is using a very vague description, it's not really telling us formally what I'm trying to say here, is that sort of a natural obstacle to the existence of a very large flow is the capacity of the edges that go from L to R, as we have just shown in this, or illustrated in this figure. So the obstacle to existence large flow is the capacity of edges from L to R. Yeah, this makes intuitively totally sense. More formally, this leads to what we call ST cuts. So this leads to the following definition. A so-called T-cut of a network G. This is just formalizing this picture on the top here with L and R of a network G equal BE as a partition of the vertices to two sets L and R is equal to B minus L, such that the source is in set L and T, the sink, is in set R. So this is what we call an ST cut. It's exactly what we just showed here on the top. Just a partitioning of your set of nodes, and partition meaning that the two sets will the union of the two sets will form the entire set, and the sets are disjoint. And in addition, we require that L will contain a source and T will contain, R will contain the sink. So exactly what we have illustrated here on top. So in the following, I will simply refer to this mostly as a cut. In a different context, cut is typically defined without dedicated vertices S and T. Here we're interested really in this very special kind of a cut, where S is contained in one part of the partition and T in the other. But I'm not going to make this distinction. Whenever I say cut, I really mean ST cut. But since this is sort of an important point here, I will write this down here. So in the following, this is simply okay. And we want to use these cuts now to upper bound the value of a flow in this network. In particular, the value of a flow that goes across such a cut. And so let's first formulate what it means when a flow sort of crosses such a cut, and how we can measure the amount of such a flow just looking at a specific cut. Okay, so the definition, next definition will introduce what we call the net flow across a cut. So the net flow across a cut R is given by following. Just write it down and I'll explain. So we use this notation F of LR. This will indicate or denote the net flow of the flow across cut LR. And we will simply sum up the flow that goes from L to R. This is EU. And subtract everything that comes back. So this part here in the net flow across a cut is everything that goes from left to right. So the value of the flow from left to right, and then we subtract everything that comes back from right to left. So looking at our example, I think I don't have flow values on this. I'll quickly add them. I think I deleted them before. 12, 18. So again, I will denote the flow always in blue in these networks, and the capacity will be black. And what else do we have? 7. Okay. So based on this definition and looking at this example, what would be the net flow across the cut that is shown in this figure? Oh, yeah. 23, exactly. This is the sum of the flow from, and this is basically the sum of these two flows, 12 and 11, and nothing comes back here on this edge, so we don't have to subtract anything. And that's why the net flow in this case is equal to 23. So in this case, F of LR is equal to simply 12 plus 11 minus, I'm just writing this explicitly, 0, which is equal to 23. Okay. Good. Then, so this is basically what we, yeah. Because we don't have any flow that goes from R to L, we have potentially one edge here that goes backwards, but it has a capacity of 9, but we haven't sent any flow around this, across this. That's why this basically, this one here is 0. Any other question? Okay, so this is basically how we quantify the flow across a cut. And we said we wanted to upper bound this somehow with the capacity. So let's see what exactly we mean with this and what we're going to use for that. And for this, we define what's called the capacity of a cut. That's a couple of definitions we have to introduce today, unfortunately. So the definition here introduces capacity of a cut. Capacity of a cut, LR, is given by and this follows exactly our initial intuition. We just sum up the capacity from edges that go from left to right. And so this seems a bit asymmetric. Before we had to sort of subtract the flow that comes back, and now we don't. We only look at capacity going in one direction, and you will see later why this makes sense. Intuitively, it sort of makes sense because this doesn't really impose a bound really on the flow. It could be 0 on the other direction, so you can't really you can use this sort of to. You would get a weaker bound. So this is simply summing up really all the capacities of edges that go from L to R. So V and L to U and R, capacity of VU. So that's, for now, it's just a definition. It's the capacity of a cut. We didn't really do anything with this yet. We will be interested in the best one of them, and the best meaning in this case in the cut with the smallest capacity, because we will use this for upper bounding our flow, and small upper bounds are good, and that's why we're looking for the smallest capacity. But this, you will see this later. For now, this is just a definition. The minimum cut minimum cut now is a cut whose capacity, in the sense of the previous definition, is the smallest over all possible cuts. So we will see later that we can use now the capacity of a cut, hence the net flow of a cut to upper bound one by the other. But really we're interested in the value of a flow, not necessarily in the, the amounts or the net flow across a cut. And the next lemma tells us basically that the two things are the same. So if you're looking at the value of a flow, we only have to look at any cuts and basically quantify the net flow of that flow, the net value of that flow across that cut to tell exactly how much the value of this flow is. And this was what we're going to use later in sort of upper bounding the value of the flow instead of just the net flow across a cut. So let me write it down, maybe then this gets more clear. If not, you can discuss that again. So lemma 26.4. So this lemma simply says that if I consider any cuts and then considering any flow, the net flow is exactly the same as the value of the flow. So for any cut, for any flow, the net flow, as we defined it above, the net flow across the cut simply the flow value. Meaning, more formally, that f of LR is equal to the value of f. Okay, so this is not only giving you an upper bound for now. So this is not giving you an upper bound on the value of the flow. It shows you that this is really the same thing. So looking at any cuts and you just consider the net flow across this cut, this is exactly the same as looking at the actual value of this flow. And this is why we introduced it. So otherwise, this wouldn't really make much sense to introduce this net flow. We will use this net flow sort of as a proxy for the value of the flow, as we will see later. And this is what we use then sort of as a intermediate quantity to upper bound the flow, the value of the flow. Let's and this is sort of one of the a bit more technical proofs, which are typically not so nice, but in this case, I want to show it because it sort of repeats a couple of definitions that we had said before. It's very simple. It's just a bit tedious to write down. It's very technical. It's just a lot of rearrangements of sums, but it uses a couple of definitions and properties of flows that we have discussed. So I think it's a good exercise to just repeat a few of the basic concepts in the context of flows. Let's see. Maybe actually one thing that I forgot to show, to mention, when we introduced, let me go quickly one step back. When we said here the capacity of a cut, we defined it simply as the sum of all capacities. Can we quickly look at the example of this? So this would mean that in this case, C of LR would be what? Can you tell me what the capacity of the cut is, just to have our example complete? Yeah. 26. Yeah, it's 26 because you're simply adding, you have two edges that go from left to right, and only those matter in terms of the definition of the capacity of a cut. The capacity of this one is 12 and the capacity of this one is 14. And therefore C of LR is simply 26. So 12 plus 14, 26. Oh yeah, okay. Okay. So let's see. This was the claim, and let's see how we can prove this. This is, as I said, a bit technical, but conceptually very, very simple. So we start by the definition. So I'll do this step by step whenever there's something not clear, or could be also just my spelling. So please just ask me. So we start by defining the value of the flow, and we have defined it basically by everything that leaves S and everything that comes back to S, minus everything that comes back. So this is the same as the sum, looking at all vertices V and taking the flow from S to V minus everything that comes back. So sum over all V and V, and then F of Vs. So this is just a definition of our flow value. Copy this to not write the same thing again. And then I'm going to just add something, and I'll ask you about this afterwards, or we can discuss it afterwards. Let me just write the following sum. Give me a second in case you're writing this. So I have here a sum over all vertices in my left partition of the nodes, except for the source vertex. And I'm summing up these values here. Can anyone tell me what that sum would be, or this value here in these brackets? Yeah. What is it? No. Actually, I'm asking even for a value. I want to have a value. So even simpler than that. Maybe read it out loud, what you see here. So this is really taking for a given vertex in or node in set L, which we fix to be U, and then we simply take all flow FUV. So that comes, sorry, yeah, that leaves U minus everything that comes into U, right? What should that be? If F is a flow, those central properties. This is why exactly why I wanted to do this flow proof. Exactly right. So it's 0 because of flow conservation. So for every vertex other than S, everything that comes in is the same as what comes out. And this is why this is I'm basically adding 0 here. This is why this still is an equality here, right? An equality. I'm adding a lot of stuff, but in fact I'm not adding anything. Okay. And then we simply expand this part here. So I'm gonna just copy this one again, first part. I'm sorry, you can't do that. So I'm just writing this in the following way. I just say again, U in L minus S. Actually, are you writing also, you also writing on tablets, or are you writing on old school notebooks? Who's using an iPad? Oh, okay, notebooks. Who's using iPads or any tablets? Oh, okay, so half roughly. So this is my first class I give on a tablet. I'm used to sort of Blackboard and whiteboard. This is really a different thing. It's very, I think since I also already don't have a very good handwriting, it looks even worse on a tablet. I think on the whiteboard it looks a bit better to my defense. So where was I? I was, yeah, expanding this. So let's do this again. Sum U in L minus S VU. Okay. Okay. So this is just expanding the second sum. I didn't do really anything here. It's just this here and then this here. Good. And then I'm just rearranging this a little bit, and you will see in a second why I do that. So again, just reordering this a little bit, and I rearrange this by following sum. I group everything by V and V, F of S comma V, Where's the other part? Plus everything but S minus S. Let me write this again a bit nicer. Minus S. So far, this is simply taking this one here and taking this one here and putting them together in the inner sum. So this sum is basically this sum, and then this is what you see, this is this here, and then this part is exactly this part here. So it's just rearranged, and then I do the same for the rest. Summarize this into minus the sum over, again, V. Let me write this in a new line. This sum here, U in minus S. Good. Does everyone see what I did here? I just rearranged this and grouped this into this different sum. So this one here is this one. And I simply grouped it with this sum here on the right. This is the same thing. One little remark here, whenever I write L minus S is sort of a bit of a sloppy notation. S is not a set, S is just a node. So I should really write, to be correct, I would have to write this one, sort of minus the set containing S. But I'm being a bit sloppy here because I think it's getting too messy if I write here even more these curly brackets in it. So I'm simply writing L minus S, even though S is not, strictly speaking, a set. Okay, and then actually, if you look at this sum, you can actually combine it. So this part here looks at all outgoing edges from S, and this looks at all outgoing edges from every other node than S in set L. So this is simply taking all vertices in L and summing up everything that's leaving this particular vertex. Let me write this down, maybe that's clear. So this is simply sum over V and V. And then I take all vertices in L, and I don't make this distinction anymore in S and not S, because I'm using both anyway in a sum. So I'm just saying this is FUV. Right? Does everyone see that this is the same here? So this one, this one. Before I just made the distinction into S and not S, and I just now don't make this distinction anymore. And I do the same thing for the second part. So I do minus, and then again the same thing, sum over all V. And again, not making the distinction into S and the rest. I take all U and L, and then I take FVU. Okay, now we're almost there. Sort of two more steps. Because now I'm trying to split this. Now we have these sums over all vertices V, and we have this partition into L and R, and that's what I'm using now. I'm writing the same thing just twice, once for L and once for R, and you will see in a minute why I do that. So this is the same as I'm writing the same thing now twice, essentially, once for L and R. I go over all V and L and use the inner sum as before, U and L, FUV. Plus, now I do the same thing for over all remaining vertices, V and R. Sorry. U and L. Okay, so this is really just splitting this sum here. This sum is split into two parts. One for L, so I'm splitting the set of vertices here into V and L and V and R, and writing the same thing, just decomposing the two sides. And I do the same thing for this for the remaining sum. So I'm saying this is minus on the one hand, we have everything from L, so V in L, U in L, FVU, minus, and now all other vertices in R, FVU. Okay, this is just, again, this is just using the fact that L and R partition V, and we write the same thing twice, basically, that we had up here. We had it once for all vertices. Now we write the same thing twice, once for all vertices in L, plus everything for the remaining vertices in R. Okay, and now it's again just a rearrangement and a little insight that I will ask you about again. So now I'm just rearranging this in the following way. Yeah, so I'm taking this one here, this sum plus this one, or minus this one. I will start with this one. Okay, I will just write this from the beginning. So I'm writing this V in R, U in L, FUV. First part minus, and then I write V in R and U in L, FVU. Okay, so this is this one is here, and this one is this one. So this is correct. Yeah, and now I'm writing the remaining two sums. So plus. So what's left is the first term, this one here, and which one, and this one here. So these are the two terms that are left now. Down. So plus and so this is the same thing, just rearranging these terms. And the reason I rearranged this is because now we can look at this one here and conclude. And conclude what? Any suggestions for that term? What it could mean? Not what it could mean, but what it could sum up to. So in both cases, you iterate over all pairs of vertices within L, within this one partition of your vertices. And on the one hand, you take FUV, and on the other hand, you take FVU. Yep. 0. This is actually always a good guess whenever I ask for a value for a complicated looking formula. It can't be 4 or 7. It's usually either 0 or something very strange. So I think 0 is always a good guess. But in this case, it makes sense, as you can see, because we're really iterating over the same pairs of vertices. So every time you have FUV here, there's sort of the reverse pair here that will lead to FVU being the same as FUV, and that's why they cancel out. And so in the end, this is basically this part will be 0. And therefore, we get what we wanted. Just rewriting this, reordering this from L to R. So I'm just flipping I'm gonna flip these two sums now, just to make it, for me, this is easier to read always to have L on the left and R the right, but obviously it's the same thing. So we'll have U and L, V and R, UV. Okay, so what is this term? And its time is not zero. This shouldn't be a trap. It's not zero, but what does this look familiar, this formula to you? So I'm not asking for a value in this case, but for a meaning. This is the net flow from L to R exactly. Yeah. This is F of LR. And this is exactly what we wanted to show. We wanted to show basically that if I look at any cut and any flow, and I look at the net flow across that cut, this is exactly the same as the value of that flow. And this is what this equation shows. We started from the value of the flow here, and we ended up here in this chain with the net flow across our cuts from L to R. And that proves this lemma. And now it will become clear why we introduced this net flow, because now we can link the capacity of a cut to the actual value of the flow. Let me just write this down, and then I think it's clear why we introduced this net flow instead of working directly with the value of a flow. So this will be corollary 6.5, which simply states that for any cut and any flow, the value of the flow is upper bounded by the capacity of the cut. And this is really what we wanted originally. Cut, LR, and any flow, F. The value of the flow is at most the capacity of that cut. And this looks weaker. It's just an upper bound now compared to our previous lemma, but it's really nice because the right-hand side now doesn't depend on the value of the flow anymore. It really is just a property of your inputs network. So it's just the capacity of a given cut L and R. And let's check that this is true in our example. Where's this example here? So in this particular case, we had F, the net flow from L to R was 23, and the capacity was 26. And the optimal value here, actually, the value of the flow was 23. So 23 is smaller or equal than 26. So in this particular example, it as expected also holds. Okay, so let's show this. This is now very easy to show based on everything that we have done so far. We have prepared this very well. So the proof goes as follows. Let's start from our previous lemma. We said that the value of a flow is equal to the net flow across our cuts. So this is basically why we used this lemma before. We related the value to the net flow. Let's write the definition of this again. So the definition of the net flow is simply by counting everything that goes from left to right minus everything that comes back. So U in L, V in R, FUV. Minus L, V in R. And now reverse, we take FVU. So this is everything that comes back. This is how we define the net flow across a cut. Then to upper bound this, we can simply drop everything that we're subtracting. We're subtracting something non-zero, non-negative, this part here. So we just drop this, and then we get an upper bound on this. So this is clearly smaller or equal than just writing the first part of this. And now we're using capacity constraints again, meaning that we can upper bound this sum by replacing the flow by the capacities of these edges. So summing over all U and L and V and R And taking the capacities from U to V will be an upper bound in this. And this is exactly the definition of the capacity of a cut. So this is C of LR. Now, basically through this net flow across the cuts, we have upper bounded the value of the flow by the capacity of that particular cut. And if for that particular cut, but this holds true for any cuts in our network and any flow F by this claim here. So this is true for any we didn't pick any specific, but for any cut and any flow, we can show that the flow, the value of that flow is upper bounded by that capacity. Sorry. 2 minutes. Okay, so this is the upper bound, and we can use this lemma now, or this corollary, the upper bounding of the maximum flow, and sort of the central theorem of this section, which is the max flow min cut theorem. I will just state it, and next time we're going to prove it. So the theorem tells us the following, and this is the central claim really. This is theorem 26.6. And this is a sort of the famous max flow min cut theorem. Which tells us that the following are equivalent. Following are equivalent, TFAE for short. A, that F is a maximum flow in our flow network, so that's what we want. So F is a maximum flow in G. Second is that the residual network has no augmenting flow. And 3, the value of the flow is actually equal to the capacity of an LR cut. So far we have upper bounded it, but in this theorem we actually find one cut with equality. So this is true for some cut LR. Okay. And next time we're gonna do sort of a visual proof of this. It's much less technical than the previous one, and very, very intuitive. And then this is basically the main part of this section. Any questions? If not, then I see you next week.